Hello, in today's lesson we will learn about the Raman effect. Raman effect is a scattering process involving a change in wavelength. This process is similar to fluorescence. You know the fluorescence lamp where ultraviolet radiation is converted to the visible part of the spectrum because the wavelength increases during the fluorescence. But there are two main differences from fluorescence. Number one, the light which is incident on the scattering material must have a wavelength that does not correspond to one of the absorption lines or bands of the material. That means the light is hitting a material and the material has certain bands which correspond to absorption lines. So we must avoid those bands while shining a beam of light on the material if we want to study the Raman effect. The intensity of light scattered in Raman effect is much less intense than those of fluorescent light. For this reason, Raman effect is rather difficult to detect. We know of the Stokes law of fluorescence, where the wavelength of the fluorescent light is always longer than the absorbed light. Raman effect is also similar to Compton effect, but the difference here is that the incident radiation is in the visible part of the electromagnetic spectrum. The mechanism is also different from that of the Compton effect. Usually, if a beam of monochromatic light passes through a transparent medium, it is scattered. Usually, the frequency of the scattered light is the same as that of the incident beam. We know that is the basic difference between reflection, refraction, where we see the light in a spatial angle. That is, the angle of incidence is equal to the angle of reflection, or we can calculate what is the angle of refraction. So this is one thing, and scattering is another thing, where light falls on a surface and it is scattered all directions. So we have to put our detector in a 4-pi geometry, and then we can measure the intensity at different solid angles. So usually if a beam of monochromatic light passes through a transparent medium, it is scattered. Usually the frequency of the light is same as that of the incident beam. However, Kramers and Heisenberg in 1925 showed, theoretically of course, that components of scattered radiation at different frequencies can be at different frequencies from that of the incident radiation. Such differences in frequencies should be present. That is what Kramers and Heisenberg calculated in 1925. Raman and Krishnan showed that the frequency nu of the intense incident light was varied. In their analysis, they varied the frequency of the incident light. Then they observed faint lines in a spectroscopic study of the scattered radiation, and they found that there are frequencies which are different from the frequency of the incident light. So that was the experimental work of Raman and Krishnan, for which they won the Nobel Prize. Professor Raman won the Nobel Prize in 1930. So that was the work. The work was that if the frequency of the intense incident light was varied, then faint lines were observed in a spectroscopic study of the scattered radiation of frequencies which are different from the incident frequency nu. Now, explanation of Raman effect is very straightforward in quantum theory. if the incident photon energy is h nu and that impinges upon an atom or molecule of the scattering medium, an energy state of this atom or molecule changes from W1 to W2. Then the energy of the scattered radiation must be h nu dash equal to h nu minus W2 minus W1. So these are the energies of the states, of the quantum states of the atom or the molecule. When h nu, this radiation, hits the molecule, the energy state of the quantum, in a quantum theory, the energy state of the molecule or atom changes from W1 to W2, discrete jump. That means the energy which is left for the outgoing radiation is h nu minus W2 minus W1. It is very simple. That means nu dash is nu minus W2 minus W1 by h. Now depending on whether W2 is greater than W1 or W2 is less than W1 or W2 is equal to W1, we can have three cases. So case 1 is if W2 minus W1 is positive. If this is positive, then nu prime is less than nu. That is lambda dash is greater than lambda. So this agrees with the Stokes law of that we discussed of fluorescence. Wavelength of the fluorescent light is always longer than the absorbed light. So this is agreeing with the Stokes law. That is, the wavelength of the scattered radiation is more than the wavelength of the incident radiation. This agrees well with the Stokes law. So this is called Stokes line. But there are two other cases. For example, W2 minus W1 can be negative. Then nu dash is greater than nu. That is, lambda dash is less than nu. So this defies Stokes law of fluorescence. So that means here we are seeing a phenomena which is different from fluorescence, and that is the speciality of Raman effect, that we also observe wavelengths which are less than the wavelength of the incident radiation. This disagrees with the Stokes law, and this is called anti-Stokes lines. And finally, if W2 minus W1 is 0, then it is the elastic scattering that we all know, that light is falling on a material and nothing happens. The wavelength remains the same, frequency remains the same, the light gets scattered. This is the Rayleigh scattering of the classical optics. So that is the central line. The central line is nu dash equal to nu. Stokes line is lambda dash greater than lambda. That agrees with the Stokes law of fluorescence. And the third case is lambda dash less than lambda, which disagrees with the Stokes law. That is it. This phenomena is not fluorescence, and this is Raman effect. Okay. An important consequence of this model is that W2 minus W1 by H must correspond to a possible emission or absorption of photon. That means it must be linked with a transition of an energy state to another energy state of the atom or molecule. It is found that these transitions are often those transitions which are actually forbidden by absorption spectrum or emission spectrum, because in those cases we have to abide by the selection rules. Delta L equal to plus minus 1 and delta J equal to 0 or plus minus 1. We all know that angular momentum can change by 0 and plus minus 1, that is the magnetic quantum number, and then the L value can change by 1, that is S, P, D, F. Those are the orbitals. S orbital can go to P, P orbital can go to D, but S orbital cannot go to D, because then L value will change by 2. So those are the selection rules for the absorption and emission spectrum. But in Raman effect, such selection rules are not necessary. The measurement of values of nu minus nu dash in Raman spectra hence gives information of the possible atomic or molecular energy levels which cannot be studied by normal techniques of emission and absorption spectroscopy. So it is very important, because normal emission and absorption spectroscopy follows the rules such as delta L equal to plus minus 1 and delta J equal to 0 plus minus 1. So that means we can get information about a limited number of energy states of molecules or atoms. But because Raman spectra, it is not necessary to follow selection rules such as this. It can give information of the possible atomic or molecular energy levels which cannot be studied by normal techniques. Okay, now Raman scattering is also polarization sensitive. So we can get informations regarding the polarization. One can provide detailed information on the orientation of molecules in crystals, how in a crystal the molecules are oriented, and also various symmetries of the vibrational modes of the molecules and atoms. So here is a schematic diagram. This is the ground state of the molecule or atom. The atom absorbs a photon. It goes up to the next energy state 0 to 1 by absorbing a photon. The atom then jumps temporarily to this state and comes back to this state. So here there is nothing happens to the state of the atom, and the emission is of the same frequency as of the incident radiation. So delta nu equal to 0. Nothing happens to the atom. The atom jumps temporarily to a virtual state and comes back to the same state. So by absorbing the photon, the atom does not change its energy state. That means the scattered radiation will have the same frequency as that of the incident radiation. Look at this diagram here. The atom jumps to a virtual state, but while returning, it returns to a state which is just above the ground state. That means here the frequency that is emitted is less, because the atom has absorbed this much of energy. So the emitted radiation will have less energy, and we know that the energy is h nu, E equal to h nu. That means nu dash is less than nu. That is the Stokes line. Because nu dash is less than nu, lambda dash is greater than lambda. So that is something which is agreeing with the Stokes law of fluorescence. So that is Stokes line. And the third case is that the atom absorbs the radiation here, and the atom was in the first state, not in the ground state. So from the first state, it jumps to a virtual state for a very short time, and then while returning, it returns to the ground state. That means nu dash is greater than nu. That means lambda dash is less than lambda. So this does not follow the Stokes law. So this is then something new, the anti-Stokes lines. See, this is Rayleigh scattering that we knew. This is Stokes that we knew from fluorescence, but this anti-Stokes lines is a specialty of Raman spectrum. Here the energy of the molecule actually reduces. The molecule was in the first excited state, but by absorbing a photon, instead of going to a higher state, it has come down to a lower state because it goes to a virtual state and then comes back. While coming back, it has crossed the first excited state and it fallen to the ground state. So that is the anti-Stokes lines, which is a specialty of Raman effect. We stop our recording here. Thank you for listening.